Hello, welcome back. What we've been discussing for a while now is how two parties can communicate securely in the presence of an adversary on their communication link. We've provided primitives for message privacy and message integrity, both in the symmetric and asymmetric settings. But in both cases, we assumed that parties are in possession of keys that they use for these primitives. Indeed, if they didn't have keys, it wouldn't be possible to get any security. We've discussed how keys are generated and created, what algorithms are used to make them, but what we haven't discussed is how they reach their endpoints. How do the parties come to possession of these keys once they're generated? And that's the whole problem of key distribution, which is a lot more complex than it may seem. And so we're going to start looking at that. We'll start with the public key setting. In some ways, the key distribution problem there is simpler and more basic. So first, let's recall what we want in terms of this distribution. So assume we've got some public key system, some RSA-based one or discrete log. And in this, Bob has a certain secret key and associated public key, which he's generated according to some prescribed method. The way we looked at and studied public key cryptography is we assumed that Alice is in possession of Bob's public key. Once she's done that, we showed how both encryption and signatures can be realized. So Bob can generate a signature on some message M using his secret key, which Alice can verify using Bob's public key. Alice can encrypt a message using Bob's public key to get a ciphertext C, receiving which Bob can decrypt and get back the message with decryption using his secret key. And these nice functionalities are enabled once Alice is in possession of this key, and the question we want to address is how she gets that. Now, a key element of that is that of authenticity. So when we ask how Alice gets that, what we mean, how does she get it with some confirmation that it really comes from this entity called Bob? And that leads us, even before we consider how to answer the question, of what one actually means by Bob, in the sense of what is an identity on the internet. So let's talk a little bit about this notion of an identity and try to understand, when we use terms like Alice and Bob, who actually are they? If we look at some kind of real world setting, we think of an identity as perhaps a name, and that name is bound to a person through some kind of societal means, such as a document. So there may be many different Alices. How does a particular Alice prove that she's the one she claims to be? By presenting, let's say, a passport or driver's license. Correspondingly, there are many different Bobs. How does one of them prove he's the right one? Well, if he shows some such document or some proof of this form, then we have created a binding between the actual person and some sort of identity encapsulated by these documents. So what is all this on the internet? Well, effectively on the internet in TLS, Bob is a server. So you can think of Bob's identity as being the high-level entity like the corporation. It's Google or Amazon or whatever. It's effectively tied to a domain name. So you can also think of the identity of Bob as just being the domain name google.com. And what we're trying to do is think about how they're bound together. But from the point of view of the crypto, we're trying to authenticate that binding. Now, it turns out that in TLS, the situation is asymmetric in the sense that usually Bob is a server and Alice is a client. And Alice is a different kind of entity. Her identity could be her IP address or domain name. She needn't be an individual, but she could be. So let's go back then to the problem, which is that we agreed that if Alice is in possession of Bob's public key, then all kinds of nice crypto is enabled, and we want to see how that happens. So the most obvious thing is that Bob just sends Alice his public key. So he may say something like, "Hi, I'm google.com, and here's the public key I generated." And now Bob can start signing, and Alice can verify, and Alice can start encrypting, and Bob can decrypt. But of course, there's a major problem with all this, which is what's usually called the entity in the middle attack. And the problem is that when Alice gets this flow, there's no proof that it comes from Bob. It could come from anyone. So suppose the adversary does exactly what Bob would do. It generates keys the same way Bob would. These are just prescribed algorithms like an RSA key generator. And it contacts Alice and says, "Here's a public key." And then it says, "I'm Bob." The result is that Alice takes this public key and thinks it belongs to Bob. So if she now starts encrypting data under it, it's the adversary that can decrypt. And if the adversary sends over a signature, then Alice believes it comes from Bob and accepts the document as having been signed for Bob, which is of course not at all what's intended. So this isn't at all what we're looking for. You might think or hope that there's some sort of mathematical way to solve that problem and convince Alice that Bob is who he claims to be. But if you start from scratch, there really isn't. We want Alice to get an authentic copy of Bob's public key. So if the key comes from Bob, then she has to have a proof to that effect. And the most popular solution is to use what's called the public key infrastructure. And what this involves is a trusted entity called a certificate authority, whose purpose is to provide this proof. And certificate is the object that constitutes that proof. Now, this isn't the only way to distribute keys with proofs of authenticity. You could think of many other things. Bob could, for example, post his key on his Facebook or on some web page which is on his domain, and the domain is trusted. Include it as an attachment in emails. There are servers where you can put keys. You might hand it to Alice in person and so forth. But certificates are what the internet is mostly running on, at least in terms of client-server interactions. There are many of these things. So here's an example, Let's Encrypt. It's a popular certificate authority. You can go there and get a free cert. If you want to set up a web server, then there's a fairly simple way to head out there and acquire a cert. Here's another one. It's in common. It's another certificate service. You can go there, pay some fees, and acquire certificates. So lots of these out there. If you look closer at Let's Encrypt, you can see that they have a certain structure. They have things called root certificates, other certificates, and we'll see how all these are used. And they cooperate with IdenTrust, which is another CA. You can look at statistics even of the usage and market share of different CAs. So here's a bunch of CAs, and you see IdenTrust seems to be the one with the largest market share as of now, with Let's Encrypt down here, but then they're somewhat tied together as well. So there are lots of choices then if you want to pick a certificate authority. So now let's see how the whole process works. What is a certificate and how do you get it? The process begins with Bob generating his keys. So he does that locally on his machine by running some key generation algorithm. Now he has a public key and he wants to have it bound to his identity. So he sends it not directly to Alice, but to a certificate authority like Let's Encrypt. The job of the CA is to perform some kind of identity check to ensure that this is really Bob's key. And once that's done, Bob has to also, sometimes at least, prove that he knows the corresponding secret key. Once the CA is assured of all of this, it issues a certificate to Bob. That certificate contains Bob's public key, but also some kind of CA-generated proof saying, I have checked that the entity called Bob, for example, google.com, is indeed the one whose public key this is, and I'm vouching for that fact. Now when Bob wants to communicate to Alice, he sends across this certificate. So Alice can check that the CA is vouching for the binding between the identity Bob, let's say google.com, and the public key in the certificate. And that's what enables Alice to trust the public key, and it now extracts that, and then all the crypto that we are interested in begins. And this process is the full set of steps that, let's say, a server would take before TLS gets enabled, with these parts being inside TLS and all of these happening ahead of time. So let's look at these steps in a little more detail. So local key generation, well, we studied lots of key generation algorithms, and which one to use will depend on the choice of system. If you've picked an RSA-based system, you'll be running an RSA key generator, setting your public key to the modulus and encryption exponent, secret key to the decryption exponent, and so forth. This is quite easy to do. There are plenty of algorithms. As an example, you can find or download OpenSSL, and within there, you just type a command, OpenSSL, generate RSA key. You tell it the name of a file to output and the desired key length, and it'll generate for you an RSA private key and corresponding public key with a modulus of this length. And it'll tell you the encryption exponent. Note this is that favorite number which we talked about a little bit before. Once you've done that, you can extract the public key. So you can look in that file and take out the public key, and that'll write the public key into this other place. And then you have that, and you're ready to start sending it to CAs for certification or whatever. If you want elliptic curve keys, same thing. You can run OpenSSL, give it some elliptic curve parameters. Here you're naming a particular group, and then again naming a file into which to place things. And here you're again extracting the public key out. So fine, so Alice can get, Bob can get keys that way. It's not the only thing. You can actually get on the internet, and there are websites where you can simply ask to generate a key. So you go there and say, just enter a key length and click go, and it'll give you back a private key and a public key. And then you can copy those out, and again you're set. So quite easy to get keys. Okay, so now the next step has been that having generated keys in this way, Bob has sent them to Let's Encrypt or whatever other certificate authority that Bob has picked. And alongside this, Bob also sends his claimed identity. So he sends a domain name like google.com, an IP address, or maybe something else. And the request is to say, bind this identity to the key I just sent. So upon receiving that request, the identity and key, the job of the CA is to first check that this claimed binding is true, that Bob really has the right to claim that identity, and if so, then it'll tie the public key to that. How this is done can vary. So for example, if Bob is a domain name, then what the CA might do is send Bob some kind of challenge, a random string, and see if he can post it on the web page of the domain. That would prove he has access to this domain, and that would prove that he owns it. If Bob is an email address, perhaps the CA will send an email to the address, and then there would be a link for Bob to click, and then that would verify that he owns the address. Perhaps you can do this verification out of BAM. Maybe Bob is actually able to supply documents. So those kinds of things would confirm identity. Another step that's usually done is that the CA has Bob either sign or decrypt something using the secret key associated to the public key he's claiming. And this is to ensure that he didn't copy someone else's public key, that he actually knows the secret key. That's kind of relevant in some applications. So once all this is done, the CA is convinced that Bob has a right to claim that identity, and it's agreed that it can bind the public key sent to that identity. Now it has to generate a proof. This is something that tells Alice, yes, I have checked all this. This proof is what's called a certificate, and it consists of two parts. There's some data, and then there's a signature. So this signature is the CA's signature on the data, which is computed under its own secret key. So here we are bootstrapping digital signatures, which is one reason we delayed the discussion of this topic until now, because certificates use digital signatures to implement them. Now, what does the data contain? Well, there are various standards for this, and you can see different choices. But typical things that go in there would, of course, be Bob's public key itself, information about it, like this is an RSA key with a modulus of the following length, etc. There would be the identity tied to the key, for example, a domain name or URL. There would be information about the CA. This is a Let's Encrypt certificate. There would be an expiry date because certificates do expire, and all kinds of potentially other stuff. Once the certificate is generated, it's simply returned to Bob. It says, here's your certificate. You can now start using it as you like. When Bob gets the certificate, now if he wants to communicate with Alice, he is going to send Alice his certificate. And what Alice is supposed to do before she starts using it to encrypt information to Bob or verify Bob's signatures is to check it. How does that work? Well, first of all, she parses it to get the data and the signature, and then she verifies the signature. This means she runs the prescribed verification algorithm of the digital signature scheme. This is the digital signature scheme in use by the CA, and for that she needs to know what the CA's public key is. So it's assumed that she has that public key. And if this checks out, then she says, okay, this certificate is looking good. There are other checks. So having expanded the cert data, she will find the public key and the identity. But she has to check, for example, the certificate date. And after all the checks pass, if they're okay, then Alice accepts it. And only now are you ready for the encryption and signatures to be developed and used. Now, it's interesting to see how all this works out in practice. You can certainly find instances, for example, where this check is not done. For example, sometimes you may have seen your browser pop up something saying this certificate has expired. So, and some browsers may unfortunately give you a choice. Do you want to continue anyway? And the bad thing to do, of course, is to click yes. But that happens. Now, one question left unanswered with this is, to perform this check, Alice needs the CA's public key. But where did it get that? How did Alice come into possession of that key? After all, the problem we're trying to solve is how do you authentically distribute public keys? And now it looks like we have a cyclic relation, because we're saying in order to get Bob's public key authentically, Alice needs to already have the CA's public key authentically. Obviously, it needs to be sure when it has the CA public key that it really belongs to the CA. So the answer is that they come embedded in software. So your browser, for example, will come equipped with copies of certain public keys of certain CAs, and so they're trusted through your trust in your browser. On Apple machines, it comes in keychain, for example. That's the basics of signatures. When they're actually deployed, there's a few other things regarding how they're set up for reasons of convenience. You will often see what are called certificate hierarchies or certificate chains. What that means is that when I have a certificate, it's actually a list of certificates inside. And the way it works is that I may get a certificate issued by, say, UCSD. They issue it, signing it with their public key. If I were to send that to someone, they would try to verify it, but for that they would need UCSD's public key. And where are they to get that? To enable that, my certificate actually also includes a certificate for UCSD, which has its public key in it, and that's certified by some higher level authority, maybe the city of San Diego, and that continues up. Rather than that, if that key is not available directly to Alice, then my cert will contain a cert for that key under some higher level authority than that, and so on. And what this means is that in the end, if you want to verify my certificate, you only need one public key trusted in your browser, and all the rest are then taken out of the cert, which contains all of this stuff, and the trust percolates down. So eventually you can trust the key associated to this because of your trust in this. Why do we do these things? Well, there's a bunch of reasons. One reason is that maybe identity and binding checks are easier for local CA. So for example, UCSD may find it easy to issue me keys because they know my identity, I'm on their payroll and things like that. The other is just to reduce some workload and spread things out. And most importantly, I suppose, is because you can't have too many keys embedded in the browser. And so they would like to minimize the number of what are called root keys. And so they want very few of them. And one way to do that is to have other certificate authorities tied in by certificates to the root ones. So it's fun to look this up. If you're on a Mac machine, you can open up Keychain. And if you open up Keychain, you can click on various things and you will see certs. So here, for example, on my machine is a cert issued by InCommon RSA Server CA to auth.ucsd.edu. What is it? It's a certificate I got when I was visiting Santa Barbara to use some internet at the university there. You can see that here, UCSB Secure Wireless. And the cert tells you the name of the CA and various information about it. Now you can click further on the cert and get more details. So if you look inside, it'll tell you here is the address of, this says UCSD, so maybe that's a different cert in any case. This tells you the address of the CA, it's in Michigan, Ann Arbor. It gives you details about the keys. So it's using, it says RSA encryption, but what that really means is RSA signatures of the style we saw. And this is the hash function being used. And it gives you expiry dates and starting dates. And it tells you what the signing algorithm is, what the encryption exponent is, and so forth. Okay, well, that kind of sets things up so that we see how certificates are expected to work on the internet. And of course, the most commonly used instance is in TLS. The server will flow its cert in any TLS connection, and you do tons of those every day. And then the communication will be based on the authenticity provided by this cert. However, when you start looking closer at certs, there are all kinds of issues that come up, which in particular make things a lot more difficult than it may seem from this preview. One of them is revocation. Often, at some point, Bob, having legitimately obtained some certificate, wants to revoke it. Perhaps his secret key was compromised, perhaps something else happened. So at that point, what does Bob do? Well, his certificate is all over the place, potentially by now. So he will send a cert, his cert, and a revocation request to the CA. The CA can check that the request came from Bob, and if that's legitimate, then it wants to revoke it. But how do you disseminate revocation information? The CA maintains something called a certificate revocation list, and it puts Bob's cert on that together with the revocation date. And this list is disseminated, so various entities are supposed to somehow acquire this list, and then before Alice accepts Bob's certificate, she really ought to check that it's not on the list. But this starts getting difficult. For example, maybe there's a time delay between revocation and acquisition of the list, or even between, it could even be that Alice isn't checking that list, something like that. There's something called an online certificate status protocol, whereby Alice doesn't look at the list, but instead goes straight to the CA with an online connection to see if this certificate is valid. This is a fair amount of work, though, to have an interaction to check every certificate. So, furthermore, this will still leave security holes. Say that Bob's secret key was compromised on a certain date. He may take a little bit of time to discover it and request a revocation. And even after the revocation is done by the CA, it may be a further time lag before Alice sees the certificate revocation list. And this will leave a period of a couple of days where the certificate might be used by an adversary. And during that time, Alice would get fooled. She would be accepting as authentic signatures that are really the adversaries, meaning she would think Bob is saying something, but it's not, it's the adversary. Or Alice might encrypt data to Bob, but the adversary can decrypt. So in practice, this is quite a bit of a problem. It's particularly a problem because these CRLs are actually quite large. There's a lot of revocation going on. So due to all these issues, there are various other mechanisms that people are considering and using to establish authenticity of certificates. One of them is certificate transparency, where it's a project of Google's where they try to fix some flaws in the SSL TLS system, and they do this by maintaining logs, and then they check the certificate logs to discard malicious certificates. In particular, many entities try to issue google.com certificates, so they're trying to catch those so people don't impersonate them. Maybe we can look at some of the other issues behind that. If you want details about how, let's say, Let's Encrypt works, you can look at their documentation and they will tell you exactly how to use their services to actually get yourself a key. This is a good discussion of what are the risks of these compromised digital certificates. So what happens when they're compromised is, for example, that you can then use exploits to get into systems and various other things. Here's another warning about digital certificate dangers and how to fight them. As they say here, the drawback to certificates is that anything goes wrong, the potential fallout can be disastrous. Criminals can create fraudulent websites that appear to be yours. They can create malware that purports to be software originating from you, and they steal credit card details and so forth. So you shouldn't underestimate the risks of these certificates being forged and going bad. And you can see that the system has a certain amount of fragility. So here they explain how it works, and then they talk about updates and somehow good practices in terms of how you use things. So here's a specific example where a certain entity set themselves up as a CA. So, but it is effectively a malicious CA. So they got themselves a certificate, and then they started issuing certificates to impersonate Google. So this is the kind of thing that certificate transparency is aiming to avoid. And but what we are seeing is that it's quite difficult. So certificate revocation is not a solved problem. And this person says, as much as I love the PKI and the mathematical security you can provide is horribly implemented in the real world. And it says if done right, it will be damn near perfect, but it's broken for all kinds of different practical reasons. And talks about the broken certificate revocation process. That's exactly what we've been looking at, how hard it is to revoke certs. Most C admins never revoke certs even when they should. People keep using revoke certs and no one notices, right? They're not checking the CRLs or whatever. And it goes on with this long list of problems. Here's another warning. This is an academic study. It says, look at HTTPS, meaning TLS, and it says the provided security is dubious because of the obscure management of digital certs. Our study considers the digital certs of the top 1 million most popular websites and shows that very few websites use certificates properly. In most cases, domain mismatches between certificates and websites are observed, and we study the legal and economic and social aspects. We identify problems with the profit-oriented attitude of CAs, right? So CAs are a business. They sell you certs, except now you have Let's Encrypt. And so all that, lots of warnings about this area. So certificates aren't the only way to disseminate public keys. So here, for example, is what PGP does. There's an online server. You can log into this SKS Open PGP server, and you can search for public keys of different entities. So for example, I typed Diffie, and I clicked, find me a keys for Diffie, and it gives them. Of course, there are many Diffies, Joe and Manuel and so forth. And I was looking for Whit Diffie. I don't even know if he's here. But in any case, apparently these people have registered keys and you could start using them.